This will be a quick trip through Chapter 6, Quantum Mechanics. So let's start off with what is light. You know light. You see it at night when you look up at the stars. You're seeing this screen by virtue of light. Well, light is actually a combination of two waveforms. One is called an electric vector, the other a magnetic vector, and that's where we get the term electromagnetic wave that propagates through space. Let's take a look at a couple of the features of the waveform. It has a wavelength, and that is simply the distance between the peak of one cycle and the peak of the adjacent cycle. So from peak to peak, the distance is called the wavelength. We also have what's known as the frequency, which is simply the number of peaks that will pass by a particular point in space in a particular period of time. The particular period in time that we use with light radiation is 1 second. So the number of peaks that go by, we call that cycles per second, or it's the period of the wave, and in electromagnetic radiation we call that hertz, and hertz simply stands for cycles per second, 1/seconds, which you will also see written as s to the -1. Now here's the continuous spectrum. I'll go through this very rapidly. If we start over here, the low energy end of the spectrum, we have the radio frequency. You can look up at the wavelength, which is given in meters in this scale, and that's 10 to the third, or in the terms of 1,000, or 1 kilometer and beyond. You can actually have radio frequencies where the wavelengths are more than 1 kilometer long. And then as we move toward the shorter wavelengths, we get to microwaves, and then we go from microwaves to the infrared. Now, all of this section of the electromagnetic spectrum is invisible to the human eyes. We can certainly detect radio waves with a number of devices, including your cell phone and a simple radio. Microwaves we're familiar with microwave ovens, then infrared, which we experience as heat, and we can use infrared to actually see in the dark. Then we have this very narrow part of the spectrum where the wavelength and frequency are what we call the visible part of the spectrum. That's what you and I have evolved to see in. Then we have the ultraviolet part of the spectrum. This is the part that gives you a suntan or a sunburn when you lay out in the sun. X-rays, which have a lot more energy, very short wavelengths, but they're very penetrative rays, and you can actually see skeletal structure with X-rays. And then the highest region of the electromagnetic spectrum, highest in terms of energy, shortest in terms of wavelength, the highest in terms of frequency, are the gamma rays. So we have very high energy down here, and very low energy over here on the radio wave end of the spectrum, and everything in between. So it goes radio low, microwave next, infrared, then visible, ultraviolet, X-rays, and gamma rays are the highest energy. Within the visible part of the spectrum, you have red being the lowest. We've measured this wavelength in nanometers at 750 nanometers, down to violet, and violet is at 400 nanometers. So if I were to ask you which wavelength on the visible part of the spectrum was the lowest energy, you would tell me red. And if I asked you for the highest energy, you would tell me violet. Roy G. Biv, to try and remember this, and that just stands for red, orange, yellow, green, indigo. Who knew that was indigo? And finally, violet is right here. So Roy G. Biv says red, orange, yellow, green, blue, indigo, and violet. Red being the lowest energy and violet being the highest energy in the visible part of the spectrum. All right, I'm going to show you the relationship between wavelength and frequency. The longer the wavelength, the lower the frequency. The lower the frequency, the lower the energy. So here we go. Long wavelength first. Peak, peak. Every time I called out a peak, Well, that actually represented just one cycle. So every time I call out 2 peaks, that is one cycle of that particular wave. So let's go up top. Peak, peak, peak. The cycles came by a little bit faster that time because the wavelength was shorter. And here we have the shortest wavelength. Peak, 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 peak. So what we discover is that the wavelength and the frequency are inversely proportional. So here is that relationship between wavelength and frequency. The little nu here, the lowercase Greek symbol nu, is equal to the speed of light, or the velocity of the waveform, divided by the wavelength. And in the electromagnetic spectrum, our wavelength is always in meters. The speed of light will be given to you on the test. It's a constant, 3 × 10⁸ meters per second. And then frequency is just the number of peaks that go by a point in space in 1 second. So it's 1 over seconds. If I rearrange that equation, here's what we see. The speed of light, the velocity of electromagnetic wave radiation, is equal to the frequency of the radiation times the wavelength. And so this is an inversely proportional, or an indirectly proportional relationship. As the frequency gets higher, the wavelength gets lower, and vice versa. If we were to do that the other way, as the wavelength gets longer, the frequency gets lower. So we have this inversely proportional relationship between frequency and wavelength, and you need to have this equation committed to memory. You will be expected to solve problems like this. A microwave oven uses a frequency of 2.45 times 10 to the 9th hertz, that's cycles per second. Calculate the wavelength of the microwave radiation used by the oven. So in this case, we start out with the equation that you've memorized, which is frequency is equal to c over lambda, and we simply solve for lambda. And if we solve for lambda, we wind up with the wavelength, and that's going to be in meters, is equal to the speed of light divided by the frequency. And hertz, the unit frequency, is just cycles per second. So you would go ahead and you would simply plug in the values, 3 × 10 to the 8th meters per second divided by the frequency, which is given in the problem, 2.45 times 10 to the 9th hertz. And remember, a hertz is just 1 over seconds. It's also often represented as just s to the -1. You would do the math and you would come out with a solution in meters, and I'll let you take care of that. All right. So the energy relationships for electromagnetic radiation are this. Thanks to Max Planck, we can calculate the energy of a single photon of a particular wavelength of energy using this expression. Now, H is Planck's constant, and it's this value, 6.626 times 10 to the -34 joules times seconds, times the frequency. And you remember frequency, it's 1 over seconds of the units on frequency. Now, because the frequency is equal to c over lambda from the previous slide, I can simply substitute c over lambda with Planck's constant in the numerator, and I can get the energy of a single photon using that expression, in case I didn't give you the frequency. Now you could go ahead, solve for the frequency first, and then plug that into this expression, solve for the energy of the photon. Just make sure that whatever units of wavelength I give you, that you convert it into meters first. Remember that Einstein was given the Nobel Prize for explaining the photoelectric effect. Let's talk about line spectrum. So a line spectrum is a set of frequencies that are associated with particular elements. If I were to take a sodium salt and I were to throw it into a flame, I would get a characteristic line spectrum of a frequency. That frequency would, in the visible range, would always burn yellow to our eyes. That's what we would see. If, on the other hand, I took a tube full of hydrogen gas and I were to energize that with an electric current, it would excite and it would produce these four discrete lines. Let's talk about the quantization of energy. Now, you don't have any difficulty imagining a minimum quantity of mass for any particular substance. So the minimum mass of sugar would be a sugar molecule. Human beings thought for a long time that energy was different than a quantity like mass. They thought it was continuous and not quantized. So stair steps represent quantized values. So for instance, what this says is you can have, let's say, step 1, step 2, step 3, step 4, but you can't have step 1.5 or step 2.5. That is, energy comes in these levels that are discrete whole numbers. So we have energy level 1 and energy level 2, but not energy level 2.5. These are known as quanta of energy. Niels Bohr came up with this model of the atom to help explain the phenomenon of line spectrum. And it makes a relationship between the atomic structure for each individual element and the line spectrum produced when those elements are excited by, let's say, putting them in a flame or exciting them with an electric current. And this is the explanation. What he said was, when you excited electrons in a particular element, that electron is moved to a higher energy state. When the electron ultimately falls back to its ground state, it emits a photon of a particular frequency that is proportional to difference in the energy states between the higher energy state and the lower energy state. And we experience that as a color.